Okay. So we discussed this, the dynamical constraint. It's time to discuss the word identity. But maybe before... So, okay. Before I start with the word identities, let me mention topics that I won't cover. So there was a whole section, section 3.9, about the chiral symmetry in massless QED. I'm not sure I will be able to cover it. So I wrote a paper together with Coppetti and Omori and Wang. You can find it on the archive. And so in this paper we discussed the general framework that I introduced in the first lecture of the course. And we also discuss several features of the symmetry category that we expect there are, and as well as this relation, we comment on this relation between higher associators and anomalies. So if you want a reference for that, you can go and look at that. And also we performed the analysis in detail for the case of the chiral symmetry in massless QED. I'm not sure I'm gonna get there. It's getting late. But if I have to summarize it in a nutshell, no, we have seen the example of Eiger group. They arise from an anomaly from a conservation equation that is a bit weird. No, we have this J1, which becomes the two-group structure together with some background for the zero form symmetry, wedged with the star J2 of a one-form symmetry. No, this was the case of the two-group. No, and notice that in the two-group, this one is just a background for the zero-form symmetry. For the chiral symmetry massless QED, there is an anomaly. No, so you have an equation like this, where now there is a dynamical gauge field on this side. No, something like that. It looks something like this. No, so this one is indeed the star of a two form. No, and here you have another one. Okay. So you have another type of equation, and in this case, you obtain so typically in the literature, if you study about chiral symmetry, they would say, there is this anomaly. Chiral symmetry is not preserved. It is broken by a quantum effect because of the anomaly. However, if you are on a space-time that doesn't have two cycles, you can still use it because this term will be effectively zero, and for this reason you can still you still have some selection rules on your correlators that come from chiral symmetry. No, and it was Tuft that first realized that this was happening. No, and so like people in particle theory, they have used chiral symmetry as if it was a symmetry all the time. No, because they say, well, look, you are local, everything is flat, this is zero. So and indeed the selection rules from chiral symmetry work. No, so we are in a situation like in the Ising model, where there are some correlation functions that have some word identity that is unexplained. No, it's explained by some hand waving arguments. No, like this is zero, but it's like the question is there is it really a symmetry, And also like there are arguments that say but chiral symmetry has too much along an RG flow, no, and there is this argument about the pion Lagrangian, no, and well, but is it a symmetry or not? No, like you use it as if it is a symmetry, but it is violated by quantum effects. So what is going on, no? And Shao and collaborators, as well as Omori and Cordova, simultaneously again, came up with an explanation. So you can save chiral symmetry using a topological defect that is non-invertible. No? So very quickly, the idea is as follows. I won't have the time to cover the whole paper, but like, because you see, like in this paper, we take this non-invertible defect and we compute the F symbols for that. so it's well, it's a nice effort in the direction of studying the higher structure of the category, but I won't have time to cover it. So however, just quickly, how do you save the day in this context? No, you have your massless QED, so it's something like this. You have Maxwell, no? We've wrote it several times, no? And then you couple it to some Dirac fermion, no? In the with the unit charge, no? This is massless QED. And then you have a chiral you have a chiral current which comes from the chiral rotation of this psi, no? So it's a transformation that goes like, I don't know, e to the alpha gamma 5 some psi, no? Acting on psi, no? And this current is this current, and you find that there is a tufta, there is an ABJ anomaly, it's called, that give rise to this anomalous conservation equation for this current, no? But how do we interpret this current? Well, the idea is if you want to insert an operator, a topological defect that implements a chiral rotation, what would you do is you just try to insert this thing, this defect, no, along a three-dimensional cycle, no? So this would be if you thought that the chiral symmetry was a symmetry, and you want to implement it with a topological defect, this is the transformation that you would insert along a three-manifold, no? However, the fact that the current is not conserved, so d of J1 chiral is equal to this expression, says that this operator is not a topological interface between QED and QED. So it's not mapping you from QED to QED, but it is mapping you to QED plus, no, I theta over 8 pi squared integral of F2 wedge F2. No? So it still gives rise to a topological interface, but this topological interface just shift QED by a term, which is still a topological term, no? But it gives rise to a different theory. This theory has a different value of decoupling. There is a shift in what is called the theta angle, no? And the fact that there is this topological interface can be interpreted as the fact that there is not a sensible theta angle in QED, because you can always shift it by means of this topological interface, no? So if you want to go back, there must be a way, no, to find another interface here that takes you back to QED and that is topological, no? And so a very nice idea, no, is that you see what you want is you want something that can get rid of this term, no? And the idea is to take a topological field theory that you stack parallel here, which is such that it has an anomaly, so it comes attached with a phase, which is equal and opposite to this contribution. So that when you compose the theta rotation with this anomalous interface, with this theory, you can cancel this term, no? So the theory that you are after is for an example, well, is a three-dimensional theory, no? Three-dimensional topological theory that must have a one-form symmetry Zn with an anomaly that can match this coefficient for some fixed value of the theta angle. No, you cannot do it for all the theta angles simultaneously, and you change theta, you change the three-dimensional theory that you are coupling to this setup, no? And surprisingly, you can do it. There is a family of TFTs that can satisfy this constraint, and therefore there is a topological defect that does it. The original papers where this was constructed was this paper by Cordova and Omori, and then I think maybe Choi Lam Shao. Again, something like 2 years ago, no? And the theory that they find to stack here is essentially a version, you know, like if you want to write F2 wedge F2 as the differential of something, you can think of it as if it is the differential of a Chern-Simons term, no? Something like this, no? And so based on this idea, they say, okay, let's take a three-dimensional theory that is like a Chern-Simons theory, no? And see whether if we add it to this, if we stack it here and we identify the various fields correctly, we can save the day. However, and indeed, like the 3D theory that you obtain is something that looks like this. No? So you have to stack to your defect a three-dimensional Chern-Simons-like theory, something that looks like this, no? Where you take some fields that live only on the surface, and you couple them to the bulk curvature in this way, no? So you end up with a defect that can implement a chiral rotation like this, but it is a defect that is obtained by means of composing, let's call it, I don't know, P over N of sigma 3, is the composition of that chiral rotation that I wrote above, so something like this. This wannabe chiral rotation stacked with a copy of this three-dimensional theory that depends on the choice of N and P, and is coupled to the bulk magnetic one-form symmetry, no? So you have a defect which is the composition of your original chiral rotation, no, and a three-dimensional TFT. And the fact that the three-dimensional TFT is sensible to the background is related to the fact that its lines, the lines that live on the word volume of this three-dimensional TFT, they are in a twisted sector for the magnetic one-form symmetry of the bulk theory. So this gives rise to a very rich structure, And I'm saying this very quickly now because during the break I got a question about is this construction of the duality defect all there is, or are there other constructions? There are other constructions. This is an example. Small a is not related to the bulk. Yeah, it's a different. It's a different. I should have called it C. Sorry, I'm improvising. So yes. Okay, and it's integrated here. It doesn't live in the bulk. It's supported only on the word volume of the defect. No? And so, like in a sense, this example is very interesting because it says that you can construct new topological defects in your theory by just stacking on anomalous symmetries possible topological field theory that can absorb their anomalies. No, so there is a very interesting game to play there, and um, we have some applications. For instance, also in axion Maxwell theory, there are examples that you can play with in a similar way. But I won't discuss them. I just wanted to mention this because I want you to go home not thinking that the duality is the only thing there is. Okay. There are also more general things. This one, for instance, is a collection. No, you have a collection of defects which is parameterized by Q mod Z. There are infinitely many of them, and they have interesting fusion rules. No, that takes two of them into 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 products. No? So this generalizes the one that we have seen so far. No? Okay, now that I mentioned this is one topic that I omit, more or less. And then there is another topic that I will omit more seriously because now I at least sketched what is this about, which is the topic of the symmetry TFT. It's very nice, it's very powerful, and I invite you to study it. And there are various references about it, but one which is extremely nice is a series of notes by Dan Fried in the Simons lectures, which we published in November of this year, so like a month ago, no? And he spent something like 100 pages explaining it. So I invite you to look at it because it's really nice. And there are also various other papers and where this concept appeared, and I gave references during the discussion session about that. So please ask your colleagues if you have missed that, or write me an email. I'd be happy to mention those. No, or look at the references there. No, okay. So now we can go and study what happens for word identities in general in this context. Yes. This one, yes. This one is correlated to theta. No. There is a construction that uses a U1, but it was discussed in a paper by Argurio and collaborators earlier this year, and they do it, but the price to pay is that the theory that you stack here doesn't have a finite partition function. It has to be regularized, and it doesn't have a finite Hilbert space either, so it's not strictly speaking a TFT according to Attia. So it's possible to do it, but you have to use these non-compact TFTs, and it's something like a BF. Yes, exactly. I refer you to their papers for more details, but the effect eventually is essentially the same. So like having Q mod Z is the same as having a circle. No. With this construction, no. With their construction, you can include the irrational shifts. Yes. So, Last section, word identities. So if we have these topological defects and they are non-invertible, we can use them to constrain observables in many ways, but they are hard to detect. No? So because we are studying quantum field theory since 200 years, more, no, maybe less, but we were studying quantum field theory since a long time, say, and if it was easy to detect them, we would have found them, no? So they require either extended heavy defects or a topology in space-time. No? So we've seen higher p-form symmetries, they act on extended operators. They don't act on points. No? And having an extended operator, we saw when we defined the 't Hooft line, no, is the same as removing a cylinder from space-time. So it is essentially the same as giving space-time a topology. No? And so if you want to see these lines, if you want to see the effect of these gadgets, you need to have some topology in space-time, which is something that happens, for instance, when you study, I don't know, CFT, we've seen it. If we put the CFT on a torus, no, we can see the consequences of this non-invertible duality defect, this Kramers-Vanier duality defect. No? If we have it on flat space-time, it's not enough to obtain something interesting out of it. No? So if we want Ward-Takahashi identities, then we want either one or the other. No? So for example, you can consider correlation functions of operators that are inserted on a sphere, on an S4, say, I don't know, or SD, if you are in a d-dimensional quantum field theory. No? So in this case, you would consider, I don't know, correlation. If I don't know, if you have a collection of point operators like this, no, inserted at various points of your sphere, no. What type of Ward-Takahashi identity can you obtain if you have one of these topological defects? Well, it's the same type of philosophy. So it's an SD. So say that we want something that acts on the points. So we have to divide by the quantum dimension, which will be something like the value of the defect on a d-1 dimensional sphere, no? In order to be able to bubble it out from a point. No? So and you can create it out of the vacuum, no? And now it is supported on a d-1 dimensional sphere, no? At the price of dividing by its quantum dimension. No? And now you can consider sliding it across the sphere, and similarly as what we have done in the context of the word identities in 2 dimensions, no? Whenever we have a topological defect, no? You can consider taking this circle, extend it around the sphere, no? And the pictures that you will obtain, it looks something like this, no? You have I don't know, in this context, that one was over there, something like this. No? I'm taking this, I'm extending it around the sphere, no? whenever I have an operator inserted at that point, I surround it, no? And you see, all the time the defect goes against itself, we have a fusion channel, no? And behind it, it's just encircle an equator of this higher dimensional sphere. And so eventually, what you end up with is something that has the action of the defect on the local point operator, because we are surrounding it. Then whatever is in the fusion channel connecting them, no? And when these lines will meet together with our circle, no? Upon shrinking it and bringing it up here, no? We have fused all those defects against themselves, and we have obtained some non-trivial defect here if there is a non-trivial fusion channel, okay? And then we can take this circle and shrinking back to a point. We end up, and when we do that, we can get a contribution of the quantum dimension that simplifies this. And so in general, you get an identity of this kind. So this would be your operators that you started from, no? Now they are in possible twisted sectors by the action of the defect, and they can join at a topological point here, no? So for instance, on the sphere, this is the most general type of Ward-Takahashi identity that you can obtain from a topological defect of codimension 1, no? So in the case of the duality defects that we have observed, no, there is no such a topological point, and these lines can be disconnected if you are acting on local operators. And the duality just takes a given field to its dual image. Okay. So if you have a theory that has an interesting duality, there are many examples in supersymmetric models. For instance, Super Young-Mills theory with 16 conserved supercharges has an interesting map which is called S-duality. And you can construct for special values of decoupling, like we did in the case of Maxwell theory, duality defect in that context, where you would have word identities of this type, which are just an expression of the duality of the field theory. No? Now, of course, if you were to insert a line in this correlator, I don't know, you choose to insert some W which is charged with respect, which still has a crossing action with respect to this surface, no? Whenever you insert a W, then moving around the circle, you will get it dressed by some other operators, which generalize. You remember we discussed the order-disorder transition in case of lines. No, we have a line here, and this one becomes a different line with a surface attached. No. So this surface here would just end up filling this bubble, no, when we slide the defect around it, and so you end up with a generalization in the context of charged lines or charged Higher operators, Higher extended operators that look like this if you have a crossing action. No, this one, by the way, was an example of a crossing action. Remember we discussed this. That there were linking action and crossing actions. This would be an example of a crossing action. So on the sphere, this is what can happen. But you remember a place where we got a lot of mileage was the torus, no? So a nice question is there is there something? How do we generalize a torus in higher dimensions? So say we are in 4 dimensions and we have one of these duality defects. What would be a manifold that we can use to show that they are there, like we did with the torus? No, what would be a manifold that we can use? And so the torus is just the product of two circles, no, in 2 dimensions, no. So if you want something that generalizes it in 4 dimensions, a possible case is the product of two spheres, no. And this is a good example because the background fields for the zero-form symmetries in 2 dimensions are one-dimensional gauge fields, and so you can insert them along the S1s and get twisted partition functions. And similarly, in 4 dimensions, the background fields for the one-form symmetries are two-form symmetry backgrounds, and so you can insert them on the S2s. You can turn on backgrounds on the S2s. So this is a good example where we can see whether there is some more interesting word identity that can arise from the existence of a topological defect, no? And I want to conclude my lecture by illustrating this example of word identity, no? So the exercise is non-trivial because we want to draw a 4-dimensional space. No? Because like in the torus, it was so nice, no? It was so easy. It was we could just move our line around, and now we want to learn how to draw S2 times S2, no? So how to draw S2 times S2? Maybe like so. This is a trick that I learned from a book by topologists. Topologists in the 80s were probably high on acid. I'm recorded, but so they come up with a very nice way of describing four manifolds, which consists in drawing them, thinking of drawing them in time. So if you want to draw a 4-manifold, you know that you can draw a 3-manifold. You can do 3-dimensional drawings, no? So you can draw a 3-dimensional picture and then draw the evolution of it in different colors, no? So for instance, if you want to draw the intersection of two planes in R4, therefore two planes would intersect generically at a point, no? So you know how to draw a plane, that's fine, no? And then for the other plane, you cannot draw it because you need an extra dimension, but you can draw one of its 2 dimensions, no? So let's draw one of its 2 dimensions, no? This would be it. It intersects the other plane at a point, no? And then we can use time to draw the other direction. So we draw the past, we have to draw it in red, no? Because it's in the infrared, no? No, what is like this? And the future we draw it in blue, no? And so now I draw the 2 planes intersecting in R4, no? This is in red I draw the past, in blue I draw the future, and this in white is the 3-dimensional slice of this 4-dimensional configuration. Okay. So now we can graduate and try to draw S2 times S2. No? How do we draw? Well, let's start. How do we draw? We know how to draw S2, so that's fine. No, this is relatively easy. No. Now we want to draw S2 times S1. That's a bit more challenging. No. So how do we draw S1 in a way which is convenient? No, you can draw S1 as an interval where you identify the 2 points. No? A circle is an interval where you have identified the 2 ending points. Okay? So we have an interval, and we identify the 2 points. But now this S1 is multiplied by an S2. No? So S1 times S2 looks like this. There is an empty sphere in the center. This interval is our S1. The inner sphere is identified with the outer sphere. No? So if I take something and I throw it out this way, it will come back in here. Okay? So this is a picture of S1 times S2. Okay? Now, we need to add time to draw S2 times S2. Okay? So that's a bit more tricky, but it can come in handy to remind ourselves that we can draw S2, no? We can draw S2 as a circle that shrinks at 2 points of an interval. So you see, I mean, this is not really an S2. Well, it's topologically an S2, let's say, no? But if I had to draw a sphere, I could think of it as a circle that shrinks at a point at an interval, grows, and then shrinks back again. Okay? So if I want to draw an S2 in time, this is how I can do it. No? So you have to imagine, I won't draw it because it would become too messy, but you have to imagine that this interval, which was our circle, is shrinking in that direction, and also in a direction that goes inside the wall. Okay? So that it gives rise to an S2 in time. Okay? Is it okay? So the idea is that these 2 points are identified. So this is a circle, no? And this circle is like this slice in this picture. But then we have a time evolution here and a time evolution there, no? So that now here we have just drawn this interval. Okay? So at this point, we will just have a copy of the inner sphere. At that point, we have a copy of the inner sphere. And as we go out, then this space develops. Okay? Yes. Yes, it's like a thick, like it's literally, it's like a sphere where you have carved out a ball, no? Which is shrinking and shrinking on the other side. No? But you have identified the inner with the outer of it. So you have, which is a bit tricky to visualize, but we can imagine it. No, we can think that this surface is attached to that one. No, so now we know how to draw it, and so we can consider doing a manipulation like that, where we bubble out our topological defect, but now in a space which is 4-dimensional and has some non-trivial topology. Okay? And then we can go to lunch. So instead of drawing it in 4 dimensions, which would require too much time and would make the food cold, I will draw it in a slice, like this. Okay, so this is a 2-dimensional slice of this space. Okay? And I won't insert anything now, like we did in the torus, no? So there is nothing inserted. Of course, you can decorate it with inserting something, but I won't do it now. So we bubble out our defects here. We normalize by the dimension, no? Now we're bubbling out, it's in 4 dimensions, it's an S3, no? And now, you see, using the topology, you can take the defect here, and it will come back here. No, it's still like, of course you have to imagine that it is a sphere, but same trick. And now, well, now there is a fusion channel here that we can exploit, no? And so we fuse it against itself, and it will give rise to some intersections, and there will be a line here. No? Here I'm using the fusion rule, say n bar equal condensate. No? Condensate of this Zn1 from symmetry, say. No? So C here, C is your condensate, no? And these blue dots here represent some topological lines that live inside of your condensate, okay, which are the morphisms, if you like, by which the condensate can end on one of these non-invertible defects. No? Like, locally, in one higher dimensions, they would look like this. No? This is your condensate, and here is a line. Okay, so this is this point, but in a different projection. Okay. Now we have more topology to play with. Have more topology to play with, because we haven't used the fact that we can move freely our defect in this region. And we can exploit that to generate another fusion channel. This is our friend the condensate. These are the topological lines. But now we take this part and this part, and we deform it like this. Topological defects make these sounds when you deform them. But okay, like this, no? And now, again, here, we have a similar fusion channel like that, no? Remember, you have always to normalize by the quantum dimension, no? And when we do it, we end up with something like this. Here we have inserted the condensate. And now, by this fusion, we have another configuration here, where we have another condensate. No, so this is, I don't know how to call them. Maybe we can call it, this we call C, this we call C prime, this line we call L, and this line we call L prime. No? What is remarkable, you see, you don't see it because we are drawing just this slice, but this line is a loop, and this condensate is attaching on this S3 along a disk which is bounding this loop. Okay? You have to remember that these lines are loops. Okay? Two of them. And now, again, divide by the quantum dimension. And now, well, now maybe it's hard to see it, but this red surface, the surface of our duality defect, has the topology of a sphere again. How do we see it? Well, you see, remember that this inner circle is identified with the outer one, and so we can take this whole thing, this whole component of the defect, move it in through this inner circle, and make it come out from the outer one. No? So if we do that, the result, no, we take, say, this line here is going to appear here. No? This line that was going in is just this line, so it's here, and then this line ended on this one, no? So it's like this. So performing this manipulation, we have brought this one in, but look at this point, no? When you move it in, it will come out the other side, no? So this one, this one is here, that one is there, and now the condensate is extended in the other direction, no? While here, it is still in the same place. This is C, this is C prime, this is L, and this is L prime. And L and L prime are still loops, as before, because we haven't done anything. We just used the topology of this interesting four-dimensional space to just fold the defect and show that after this fusion, we got a sphere back, okay? Now it is a sphere, so we can shrink it back, no? So we can take this and show that it is indeed a sphere, no? And along the way, well, this condensate will stretch like this. And this one also stays, in this one will stay put like this. So here we have C, and here we have C prime. Okay, and this is divided by 1 over the dimension of S3. Okay, at this point, we want to shrink this sphere back to 0 size, no? Want to shrink that sphere back to 0 size, no? And when we do that, we have to use the fact that the lines now, the lines that you don't see, the lines corresponding to these 4 points in this drawing, they form a Hopf link in the dimensions that I'm not drawing in the board, no? A Hopf link is a configuration like this. This is L, and this one is L prime. I'm not drawing it in the board because I cannot, I'm not good, but they form a Hopf link. And when we shrink the sphere to 0 size, since they form a Hopf link, we have to undo the link, no? And this can come with a cost when we do it. The cost is a phase, which is capturing the braiding of these 2 lines. So as a result, we obtain something that looks like this. No? They look like this. We have our C here. We have our C prime there. Sorry, like this. I'm drawing it in the wrong place, like this. This is our C, and this is our C prime, no? And out of this, we get this braiding phase, no? And notice that we have absorbed the quantum dimension because we have shrunk the sphere to 0 size, no? Now, if you remember the definitions of the condensate that I had on the board before, now we can rewrite it, no? So this one was the partition function of our theory on S2 times S2, this one. We do all the topological manipulation, we arrive here. This one is the same partition function, no? It's a sum over the B and C in this H2, no? Of S2 times S2, coefficients in Zn, no? Of the partition function where we have now decorated the two spheres with B and C, no? So in particular, in the H2 of S2 times S2, there are only 2 copies, so we can just write it as this. No, there are only two non-trivial two cycles in S2 times S2, S2 and S2. Okay. So and we are summing over B and C, which are discrete gauge fields, so they are valued in Zn, inserted over these two S2s. The blue Hopf link measures a possible torsion term, which is related to the cap product of U, B, and C. No? So, what? Yes, this is the Hopf link, and the price of undoing the Hopf link is this phase. Yes. So, if you look at this expression, you see that this is the same as gauging the Zn one-form symmetry of the theory you started from. Because gauging a Zn one-form symmetry is exactly summing over all possible decorations of your background by the corresponding one-form symmetry fluxes. So this is exactly the same equation that we got when we studied the effect of having the non-invertible duality defect on the torus for the Ising model. The same identical effect in 2 dimensions, now extended in 4 dimensions. In one case, it was stating that the two theories, the one with Z2 gauged and the Z2 ungauged, the Ising and the Ising mod Z2 were the same. Here, we are saying we have a duality defect that implements the gauging of this Zn one-form symmetry. Well, just from the existence of the duality defect, by a series of topological manipulation, we can see the duality. Okay? Yes? Oh, but look, there are 2 condensates here. The condensates themselves, they are supported on these 3 manifolds, and they correspond to summing over the specific backgrounds, no? The condensate is a gauging of the original Zn. The fact that the fusion is such that 2 condensates appear becomes equivalent to gauging the original Zn because you hit both spheres eventually. We are not gauging the condensations, no. We are not. The condensation is a gauging of the one-form symmetry on that specific subspace, and they emerge from the fusion rule of our defect with itself, no? And the topology of this space is such that we can fold the defects against it, no? So many ways as to insert this Heidegger gauging operation on all possible subspace in all possible ways. And so that eventually we end up with something which is the same as gauging the symmetry on the whole space. No? So in a sense, does it answer the question? So the idea is that, and there is a nice interpretation of this, but I won't tell you the details because it's time to eat. There is a nice interpretation of this. Whenever you have a description of your manifold in terms of Bordisms, all the Bordisms that you can construct can be decorated by morphism in the symmetry category, so that eventually you can read off the word identities just out of the decomposition into Bordisms of your 4 manifolds or your Heidegger manifolds. No? So there is a deep interplay indeed between topology and the possible consequences of having a generalized symmetry of this kind. Okay, so we've seen, no, in the course, many of the features of the topological lines in 2-dimensional theories can be generalized to higher dimensions, no? But the main difference is that while the fusion ring and the various features of the lines are captured by Hilbert spaces of topological points, in the case of higher dimensional symmetries, the junctions and the fusions can occur on higher dimensional spaces, no? And therefore, the role of the topological points is now replaced by topological field theories supported on these intersections that have non-trivial effect on the observables of the theory. Okay, so for stating that a theory has a duality, it was very non-trivial. It's very non-trivial, like the fact that, okay, for Maxwell theory, it's relatively simple to show, we did it, but in general, it's very non-trivial to show that a theory has a duality, and typically people have to compute observable on one side and on the other side of the duality to show that this happens. If you find a duality defect like this, then the identity of the partition functions is just a consequence of the fact that this defect exists, and you can predict all of them in this way, in one shot. No? So this is just an example of the power of the formalism. And also, we've seen there are constraints on RG flows, like the ones that we've seen in 2 dimensions, that can be generalized in higher dimensions if you know that the RG flow is consistent and compatible with the higher structure of your symmetry category. No? And this interplay between constraints on RG flow and higher structure of symmetries are just start being explored right now. No? So we knew, for instance, we discussed about the anomalies. The anomalies have to match along RG flows. If you have a higher structure, like the higher group, this gives you extra data that has to match along the RG flow. The structure group constants, they are extra data on top of the anomaly that will match. And if you have one of these higher symmetries with fusion channels and these TFT, topological field theory coefficients, the whole structure has to match. And that is an incredible constraint. And indeed, we started using it, you can start using it to probe very non-trivial RG flows. RG flows from gauge theories in the ultraviolet and sigma models in the infrared. And yes, so I find it extremely interesting. I hope I conveyed my enthusiasm on the topic. And I hope, of course, I wasn't able to discuss everything that I wanted, and there are many details that I swept under rugs, of various kinds. But I hope that I was able to motivate you enough to dive deep in the literature and learn about this topic some more. Okay, so thank you for surviving till this point. I hope you enjoyed.